Hello, welcome everyone. My name is Isaac Vallenrat. I'm a specialist solutions architect on the EC2 Spot team, and this is Safe Cost Running Kubernetes Clusters with EC2 Spot instances. On the agenda for today, I'm going to start with an overview of Amazon EC2 Spot instances. Then I'll do a recap of Amazon EKS, which is our managed Kubernetes service. And then we'll get into the details of how to use Spot instances on Kubernetes clusters. So how can we launch and register our Spot instances on the cluster? How can we scale our applications and the underlying EC2 instances? How can I influence Spot scheduling? So on a cluster that combines on-demand and Spot instances, I can control if I want applications to run on a specific purchase option. How can I handle EC2 Spot interruptions? And then a set of helpful tools and techniques to fine-tune my experience. I'll cover then a live demo so you can see how everything ties together. And then I'll recap with main takeaways and questions and answers. We're going to have moderators during the session. So if you have any question, please type it on the chat, and our moderators will be helping you out. And at the end of the session, we'll have a few minutes left. So if there are any leftover questions or any additional questions at the end, we can cover them or even look at the common questions that came up during the presentation. Let's get into it. Amazon EC2 Spot instances overview. Spot instances are a purchase option within EC2. The most popular purchase option is on-demand and is where customers start with. As a customer, you can launch on-demand instances, as many as you need, and during the time you need them, and pay for them by the second. This is great because it doesn't tie you to any commitments and is awesome for any workload that is spiky or whenever you don't have a clear amount of capacity that you are going to need for your workload. Once you have steady state usage or workloads that run 24/7 and you know your baseline, you can make a commitment with AWS for 1 or 3 years in the form of reserve instances or savings plans. And in exchange, you get some discount. And then we provide you with Spot instances. Spot instances are the spare EC2 capacity that we make available to you with an up to 90% discount compared to on-demand, with the only consideration that as this is a spare capacity, if we need to reclaim it, we'll give you a 2-minute warning and we'll get that instance from you. This means that for any workload that is flexible, fault tolerant, and stateless, you can save a significant amount of money using Spot instances. The rules of Spot are very simple. First, infrastructure. The infrastructure that powers Spot instances is the same that the one that powers on-demand and reserve instances. There is no differences at hardware level. Pricing. Pricing is based on the long-term supply and demand for each instance type on each availability zone on every region, which is what we call a Spot capacity pool. Prices are with an up to 90% discount compared to on-demand, and the average discount that you can find is around 70%. The price of the Spot instances adjusts over time based on the long-term supply and demand for each capacity pool. However, any price changes are infrequent and smooth, so you won't see spikes on pricing, and the price you're paying is predictable. You always pay the current spot price. When it comes to interruptions, they only happen when EC2 needs to reclaim capacity. If you work with Spot instances or heard about Spot instances before November 2017, you may recall they were based on bidding. So you placed a bid for spare capacity, another customer could outbid you, and it was a bit complex. So that's not the case anymore. And remember, there is no bidding on Spot. the interruptions will only happen if EC2 needs to reclaim the capacity. As Spot is spare capacity, a key best practice for you to be successful is to be flexible to use multiple instance types and multiple availability zones. That, if you remember, I said those are capacity pools. So the more instance types and availability zones you can use, the more capacity pools you can get Spot capacity from. Let's talk about interruptions. So spot instances are interruptible, and you need to use them with workloads that tolerate interruptions. However, if we look at the data for the last 3 months across all the AWS regions on EC2 Spot, we can see that less than 5% of the Spot instances were interrupted by EC2. That means that on 95% of the cases, customers were able to acquire the Spot capacity they needed, do the work they had to do with it, and terminate that capacity without being interrupted. When interruptions occur, we'll give you a 2 minutes notice. And you can build automation around that so you handle the interruptions gracefully. The interruption notice is given to you in 2 forms. One is the EC2 metadata endpoint, that is a local endpoint within every EC2 instance, the 169.254.169.254 endpoint, or via a CloudWatch event that can catch that event and trigger a Lambda function, for example, that executes interruption handling logic. The actions or the automation will change depending on your workload. So if, for example, you're running a batch workload, you can do a checkpoint. So you can bring up a new instance and repeat the work from where you left it. If you are running a web application, you want to stop sending new requests to that instance that is going to be interrupted and leverage those 2 minutes to let in-flight requests to finish. So you can gracefully remove the instance from your fleet. All this functionality is integrated with autoscaling and ELB. Or if you're running a container orchestrator, as we are talking today, and one of your instances executing your tasks or pods is going to be interrupted, you can cordon the instance so no more tasks or pods are placed on that instance, and take those 2 minutes to drain the existing pods or tasks so the scheduler can schedule replacement pods somewhere else in your cluster. Spot instances and containers are a match made in heaven. And we say so because they share a lot of common principles. They are both meant to be stateless, fault tolerant, which makes them a great fit to work together. So both Spot instances and containers are meant to be treated as cattle and no pets. This means that you can use Spot instances with your containerized workloads and run your workloads at a fraction of the cost with Spot. A great example of this is Skyscanner. Skyscanner is a travel fair aggregator website that runs their online platform on Kubernetes powered by EC2 Spot instances across multiple AWS regions. By using Spot instances, they are achieving 74% savings across all the regions where they run. So as you can see, Spot instances are a super powerful tool to achieve significant scale and savings. In order for customers to make use of Spot instances on all those Spot-friendly workloads and on an easy way, we built a lot of integrations with AWS services like EC2 Autoscaling, where I'm going to focus a bit more today, as is like a foundational service that is going to help us to bring up Spot capacity for Kubernetes. There are also integrations with Amazon ECS or Elastic Container Service, which is our own orchestrator. EKS, as we are talking about today. AWS Fargate, which is our serverless container engine, also has a Spot pricing option for Amazon ECS. Elastic Beanstalk that lets developer zip their code and upload it to Beanstalk, so it handles the deployment of the infrastructure to run it also integrates with Spot. AWS Batch for your batch workloads. SageMaker has a managed training feature on Spot instances to reduce your cost of training your machine learning models. Amazon EMR for big data, and CloudFormation to define everything with infrastructure as code, as well as Thinbox Deadline, that is a rendering service. And these are only the AWS integrations, but a lot of third parties have also built integrations with Spot. So you can leverage the savings and scale of Spot instances on all those workloads that make sense, like CI/CD with tools like Jenkins and Bamboo, or very popular tools from HashiCorp like Terraform and Packer. Big data, so Databricks, Cloudera, and Kubel also have built integrations with Spot, and then container orchestrators that also integrate very well with Spot. In order for us to launch Spot instances and help us follow best practices and be flexible to use multiple instance types and multiple availability zones, we can use EC2 autoscaling. EC2 autoscaling provides us a very easy way to achieve this. If you have used EC2 autoscaling and you're familiar with it, you probably know about launch configurations. That is the object where you configure the image for your instances to launch. And then things like your security group or your user data script that you're going to use to bootstrap your instance. Launch templates are an evolution of launch configurations with very powerful and new features like versioning, and they also allow you to use this autoscaling feature that it's called mixed instance groups, where you combine different purchase options and multiple instance types. On the screen, you can see the autoscaling console wizard to create an autoscaling group. And once we have configured our launch template, we can click on combine purchase options and instance types. Then we can configure a distribution for our instances. Optionally, we can define a base of on-demand instances. And then we can set up percentages of on-demand and Spot instances that we want once our autoscaling group grows over that base capacity. And then we can configure the Spot allocation strategy. Here is where the power comes. The allocation strategy makes autoscaling do smart decisions when picking which instance type to launch of a list of possible instance types that your workload can work with. And we have two. Capacity optimized, which is the default and recommended one, that is going to look at all your instance type selection on its availability zone and launch Spot instances from those capacity pools that have the optimal spare capacity. This way, you significantly reduce your chances of interruption. If you want to optimize for price, you have also a lowest price allocation strategy, where you can ask autoscaling to give you the n number of cheapest instances on each availability zone from your selection. Your selection of instances comes later on, as you can see on the right side of the screen. So as you scroll down on the wizard, you can see a primary instance type, in this case, an M5X large. And then the console is going to propose me a list of possible instance types that are also very likely useful for my instance, for my workload. So I can review it and add or delete instance types as I see fit. Let's look at how capacity optimize works. This is a graphical representation of an autoscaling group. In this case, it's an autoscaling group that spans through 3 availability zones. And we are asking for 12 instances. In this case, it's an autoscaling group composed by only Spot instances, as on-demand base capacity is 0, and on-demand percentage above capacity is 0. I'm telling autoscaling that I'm happy to work with R5 largest, M4 largest, and M5 largest. And for the allocation strategy, I pick up capacity optimized. If you look at the graphical representation below, you can see that on each availability zone, each instance type has a $sign and a bar. The $sign represents the price, and the bar represents the available spare capacity. As you can see, autoscaling has picked the instance type coming from the deepest pool. This means that my chances of getting interrupted are much lower. As my autoscaling group scales out, this decision is reevaluated every time it launches instances. So over time, my fleet is going to get recycled, and I'm going to be using the optimal instance types based on the available spare capacity. Okay, let's look at Amazon EKS. If we look at the high-level architecture of Kubernetes, we can see two clear separate components. One is the Kubernetes control plane, or the brain of the cluster, where the API server will interact with seeds, the scheduler logic, a set of controllers, the key value store that holds the cluster configuration. And then we have the Kubernetes nodes. The Kubernetes nodes are the EC2 instances that register to the cluster control plane that are running your applications and are executing your containers. These EC2 instances run the kubelet, which is the Kubernetes agent that registers and talks to the control plane, kubeproxy, that is a service that exposes your applications at network level, and also the container runtime that executes your containers. So in the Kubernetes nodes is where we can use EC2 Smart Instances. Amazon EKS provides you a highly available and managed Kubernetes control plane. So all the complexity of configuring, setting up, and maintaining a highly available Kubernetes control plane is removed from our customers. The experience you get is with a few console clicks or with an API call. You can bring up a Kubernetes control plane, and you get an endpoint you can point to with kubectl, and you can interact with your cluster in the same way you do with a cluster you launch on your own. Amazon EKS also provides you a feature that is called Manage Node Groups. With Manage Node Groups, EKS, with also a few clicks on the console or an API call, can bring up an autoscaling group of EC2 instances and manage the registration to Kubernetes and the lifecycle of those instances. This feature, as of today, only supports on-demand instances. However, by using EKS CTL, which is the official EKS CLI tool, we can easily bring up autoscaling groups composed by Spot instances, and this is going to be our focus today. It's also worth mentioning that Amazon EKS is Kubernetes certified and is fully conformant with upstream Kubernetes. That means that any existing tools or plugins that you use with Kubernetes outside EKS can work with Amazon EKS. The same applies for your applications. So any application running on Kubernetes on premises or on Oracle Cloud can run on Amazon EKS without any code changes. Which are the popular use cases we are seeing our customers using EKS for? So first, microservices. These are applications that are born in the cloud and that take advantage of all the features that Kubernetes provides. We're also seeing large companies to create tools on top of Kubernetes and provide Kubernetes as a platform as a service to their developers. So they abstract components from Kubernetes to the developers, and so they can focus on developing their applications. Also, legacy enterprise applications migrations, like Java applications running on the data center that follow a lift and shift pattern, they get containerized and run on EKS. And we also have a lot of customers doing machine learning with Amazon EKS with platforms like Kubeflow. No matter what use case do you have for Amazon EKS, bringing up a cluster is very easy with EKSCTL. You can see a sample command on the screen where I just call EKSCTL, create cluster. I give a name to my cluster. I define the version of Kubernetes I want to use and set up an initial node group. So I just need to sit for a few minutes and wait until the cluster comes up. Now, let's look at how can we use Amazon EC2 Spot instances on Kubernetes. In my talk, I'm going to focus on Amazon EKS and launching node groups using EKSCTL. However, all the key gotchas or all the key things you need to take into account are applicable also if you decide to run Kubernetes on top of EC2 with other tools like KOps or configuring it yourself via your preferred infrastructure as code tool. Amazon EKSCTL provides you similar experience to the experience you get with kubectl. So you can create a YAML file with your cluster definition. You can see the snippet on the screen. My cluster is named EKS Spot Tech Talk and is on the EUS1 region. And then I can define node groups. And I have a node group on the screen. The name is demo, 4 vCPUs to 16 gigs spot. And the first square, if you look at it, what we're configuring here is an EC2 autoscaling group. It's composed by only EC2 Spot instances, and I'm combining or I'm flexible to use all the instance types that you see on the screen, M5X large, M5X large, M4X large. All these instance types have the same number of virtual CPUs and the same amount of memory. And this is very important when I create my node groups. And this is relevant for Cluster Autoscaler, that is the scaling component for Kubernetes. Cluster Autoscaler assumes that all the nodes in a node group are homogeneous. So this is why it's very important that the instance types that you use here match the number of vCPUs and memory. I'm also using capacity optimized here. So autoscaling is going to give me instances from the optimal pools based on the available spare capacity. Then I can define labels. I'm defining a label lifecycle EC2 Spot and a label intent value apps. These labels are visible to Kubernetes, and they will allow me to take scheduling decisions, as you will see later on. They are similar to AWS tags, but visible to Kubernetes. And then you also have tags that you can define on the actual autoscaling group that EKSCTL will bring up. In this case, these tags are required by Cluster Autoscaler, so it allows you to scale down to 0 instances, an autoscaling group if you need to. Okay. So that's a node group, but you can combine multiple node groups on a single cluster. So I can add a second node group where I combine instance types from the same families, but 2x large. And I'm also using capacity optimized. By using multiple node groups of spot capacity with capacity optimized and different instance sizes, I'm not only getting capacity from the best pools for one selection, but for 2 selections of instances. So my fleet is stronger. And then I can also define an on-demand node group. There are some applications that I may want to run an on-demand, or I may want to use on-demand nodes to run things like core DNS that provides the DNS service to my cluster. So I can create the node group and label it accordingly with the label lifecycle. Once my file is defined, I simply call EKSCTL create cluster. I pass the file and I sit and wait for a few minutes until the cluster comes up. EKSCTL is going to generate a CloudFormation template with all my infrastructure, and is also generate all the bootstrapping automation to get your nodes registered to your Kubernetes control plane. Let's talk about scaling. So in Kubernetes, you scale two different layers. One is your application that runs in the form of pods. And the other one is the underlying EC2 infrastructure where the pods run. Let's start with the application. In the left side of the screen, you can see a definition of a deployment where I'm configuring two replicas for my application. I'm configuring the image, the container image I want to use. And there is also a section called resources where I'm specifying the requests for resources of my application. In this case, 1 vCPU and 512 megabytes of memory. This is very important because Kubernetes is going to take this into account when placing my pods on the instances, and for Kubernetes to be able to know if they fit or don't fit on the instances. So once I have my application running with horizontal pod autoscaler, which is a Kubernetes component, I can define a metric that can be a CPU metric or a memory metric or even a custom metric, and a threshold for that metric, and a minimum and maximum number of pods for my application. So my pods will be publishing metrics, and once that threshold that I define is exceeded, horizontal pod autoscaler will scale out or will scale in my number of replicas, hence scaling my application. To get into a bit more detail on the requests for my application, this is a very simplified way of how Kubernetes sees the EC2 instances. So Kubernetes knows the amount of vCPUs and memory that the instance has, and then each application requests a set of resources in terms of vCPUs and memory. This way, Kubernetes knows how or where the pods can be placed, or if there is no space and it cannot schedule more pods. This is a very simplified view. A quick note is when using Amazon EKS, or if you use the AWS VPC Container Network Interface plugin, Amazon EKS provides pods with native AWS networking, meaning that they get an IP from the VPC where the instance runs. So this means that the number of pods running on an instance is also limited by the number of network interfaces and secondary IPs that that instance type can have. But no worries, because this is all fully managed for you. Because when EKSCTL brings this up, configures this while bootstrapping the instance. Then let's look at how can we scale the underlying EC2 instances. So with Kubernetes, we are not using native scaling or AWS scaling policy. We're using Cluster Autoscaler, which is this component that is going to be watching our cluster. And whenever there are pods pending, because they don't fit on the existing nodes, it will go to the registered autoscaling groups or node groups and scale out the autoscaling group that matches the application requirements. So a new node comes in, and the pods that are pending, because they don't fit, can be scheduled on this new node. It also triggers scaling events when there are nodes underutilized. So any nodes with low utilization are removed from your fleet, and you don't have waste. Let's talk about how can you influence pod scheduling. So on a cluster that combines on-demand and Spot instances, you may have some applications that you want to run on Spot or that you're happy to run on Spot, and maybe you want to control some applications to run on demand. And you can do this in a couple of different ways. One is with taints and tolerations. When you create a node, you can taint that node with a taint. In this example, you can see it on the upper side of the screen on the snippet. Taint lifecycle, EC2 Spot, and the value is preferred no schedule. This means that any application or any pod that doesn't have a toleration for that taint will preferably be not scheduled on that instance. So if I want my application to tolerate this, I can add a toleration to the specification, and the pod will be scheduled there. This example is a preference, but you can also make it a hard requirement instead of a preference. You can also use node affinity. So by using the labels that we've defined when we created the cluster, we can specify a preference, as you can see on the left side of the screen, to schedule my pods on nodes with the label lifecycle is to spot, or a requirement, as you can see on the right side of the screen, where I want my pods to be scheduled on on-demand nodes. Now that we've seen how can we control scheduling and how can we scale applications, let's talk about interruptions. In order for you to handle spot interruptions, our development team has put together a great open source project called AWS Node Termination Handler. AWS Node Termination Handler is a Go application that gets deployed in your cluster as a daemon set, and it checks the EC2 metadata waiting for an interruption notice. When it catches an interruption notice, what it does is it cordons the node and drains the node. So no more pods are scheduled in the instance, and existing nodes, existing pods are evicted, so Kubernetes can schedule replacement pods somewhere else. Installing it is very easy with Helm, and it also has very cool features like a webhook that you can configure to send interruption events to, for example, your Slack channel. It also handles scheduled maintenance events. Those are events when you receive an email saying that you need to stop and start one of your instances because the underlying hardware needs to go through maintenance. So this project will handle all this for you. And then let's go through a set of helpful tools. So starting with pod disruption budgets. It may happen that you have a set of pods for the same application running on a Spot instance that is going to be interrupted. In order for you to gradually evict those pods to other nodes and leverage those 2 minutes warning, you can define a minimum percentage of pods for your applications that need to be available at all time. So within these 2 minutes, Kubernetes will try to respect the pod disruption budget before the instance gets interrupted. So you can leverage the 2 minutes warning to gradually move those pods. This is very powerful in combination with Cluster Over Provisioner. With Cluster Over Provisioner, you can schedule POS containers that are doing nothing on your cluster, but holding space. These pods are low priority, and they are doing nothing. That means that if any of your application pods that have higher priority need to be scheduled and there is no place on the cluster, the over-provisioning pods would be evicted and your application pods will take its place. Amazon K8s Node Trainer will have you handle AZ rebalance events for your auto-scaling groups that are not catched by the node termination handler. So these are events when if the number of instances across AZs gets imbalanced, auto-scaling will kick in to balance this. So Amazon K8s Node Trainer will help you deal with this. Then the scheduler that lets you to periodically deschedule your pods so they are rescheduled based on the optimal state of the cluster over time. And then for monitoring, Amazon CloudWatch provides you with container insights, which makes very easy for you to monitor your cluster metrics and your logs on a single place. And then during my demo, I'll be using a tool called KubeOps View, built by Henning Jacobs from the Zalando team, that it's very useful because it gives you an operational picture of your Kubernetes clusters. Let's look at the demo. Okay, so this is my Cloud9 environment that I use to do my setups and play with AWS services. And this is the configuration file for my cluster that is already deployed that you saw on the presentation. Here I can do EKSCTL, get node group, cluster, EKS, spot, tech talk. And I can see the node groups, 1, 2, 3, 4 node groups of my cluster. The way this translates in the console is, let me go to the autoscaling console. This is the new autoscaling console. I want you to show you the way to get into this console. So if you get redirected to the legacy autoscaling console that you will see in a moment, you get here a link to get into the new console. So you see what I was showing you in the presentation. I'm gonna filter my autoscaling groups because I only wanna see the Kubernetes ones, the EKSCTL ones. And I can say that EKSCTL has set an autoscaling group for each of my node groups here. I can see details like desired capacity, the name, the launch template they are using, the AMI ID. And then I can see the purchase options and instance types I was showing you before. So this is a 100% spot autoscaling group using capacity optimized. And I'm using this different list of instance types. The console experience, if I were to create this from scratch, I can go here to the instance types and I can click on redo recommendations. So as you can see, the console has brought up a list of potential instance types that I can use. And I can delete the ones I don't want. And once I'm happy, I can just update the configuration. Gonna cancel. And now I'm gonna go to GitOps View. So this is the tool developed by Henning Jacobs I was telling you about before. And this is my cluster, which is running 4 different nodes. And you can see, if you look at the bottom, the label lifecycle, on demand, easy to spot, and on demand. And I can run things on demand like Cluster Autoscaler or Core DNS, or all these applications that are serving the cluster like the metric server. And then I have my spot instances. So the first thing I want to do is I want to deploy the AWS node termination handler. And that's super easy with a simple command with Helm. So I can go here, do Helm install, click enter, and I can see the AWS node termination handler pods being scheduled one on each of the nodes because it's a daemon set. Okay, so I'm ready to handle spot interruptions. Now, let me go back to the cluster, to the workspace, and I'm gonna deploy my application. So this is my application where I have a load balancer, and it's a deployment with 2 replicas, where I have configured affinity, and I have a preference to schedule pods on nodes with the lifecycle label spot. I have also a preference to use label name spot fleet. This is because I use a spot fleet to bring up one instance because it's gonna let me reproduce an interruption. However, you need to use EC2 autoscaling to use Kubernetes. This is only for demo purposes. And then I have a requirement for this application to run on nodes with the value intent apps. It requires 1 vCPU and 512 megabytes of memory. So kubectl apply -f Monte Carlo by service YAML. That's great. And I can see that the Monte Carlo pods that are the one, so each of the square is a pod. And now I can filter, so I can see in green only the ones that are for Monte Carlo. And I can see that they were scheduled on the EC2 Spot nodes. I can go here now and scale my deployment. Carlo by service, replicas 8. So now new Monte Carlo pods will come up, and I can see that 6 got scheduled and 2 are in pending state because they don't fit on the cluster. And even if this pod, if this node is empty, as I had a requirement for those pods to be executed on a node with the label intent apps, and this one has control apps, they won't be scheduled here. So cluster autoscaler is gonna pick this up and is gonna increase the size of one of my autoscaling groups to bring up a new node so they can be scheduled. In the meantime this happens, what I'm gonna do is I'm gonna deploy over provisioner, because on a production environment, I probably don't wanna wait until a node comes up. So again, using Helm, I have configured a set of values for over provisioner. So creating the priority class with name over provisioning, value -1, the POS container, and I want it to hold 1 vCPU and 512 megabytes of memory. So I'm just gonna go here and deploy it. Awesome. So this was deployed. And I can see 8 Monte Carlo pods, 3, 3, and 2, and 2 over provisioner pods that are these pods here that are on the Spot instance. So now I'm gonna scale out the Monte Carlo application. Scale deployment, Monte Carlo by service, replicas equal 12. And what you're gonna say, what happens is not everything fits. So if you see one of the over provisioner pods have been evicted, so I have one pending, and the Monte Carlo pods took its space. So the one waiting for new nodes to come up is the over provisioner. And now to close up the demo, I want to go to my instance that I launched with Spotfleet, and I want to chase the logs of the node termination handler that ends in PQP. So, and simulate an interruption. So I'm going to go back to my workspace, kubectl, get pods. This runs on the kube system namespace. Great. So I have my node termination handler here listening, and I'm gonna go to the Spot request console where my Spotfleet runs. Spotfleet, if you're not familiar with it, is an API that we have for customers to launch Spot instances before autoscaling had all these nice features. And it's also used on very specific integrations. So when I decrease the size, what is going to happen is in a few seconds, this is going to trigger an interruption notice to this instance. You see launch mode Spotfleet. I label it accordingly, so I know which one it is. And what will happen is the pods here, the Monte Carlo pods that are running here, will be evicted once the notice comes in, and they will be rescheduled, for example, on this node that still have space. If by some reason they don't fit, the three of them don't fit, the over-provisioner pods are the ones that are gonna be evicted, and as you can see here, and the Monte Carlo pods that are the higher priority ones took its place. In the meantime, class autoscaler brings up new capacity. Okay, so hopefully this gives you a good understanding of how to use Spot instances with Kubernetes. Before I go back to the to the presentation, I want to show you very quickly one feature that you can use on the Spot request console that is called savings summary. So in savings summary, you can very quickly see how much savings are you achieving once you start using Spot instances. So you can see that in this case, I am achieving 68% savings. So as soon as you start using Spot, you can come here and see the gains. Okay, so main takeaways I'd like you to walk away with today. First, you need to be flexible to use multiple instance types. So you are able to allocate or to launch Spot capacity from multiple Spot pools. Then you need to rely on auto-scaling with the capacity optimized allocation strategy. So you select a number of instance types you are happy to work with, and the capacity optimized allocation strategy picks the optimal instance types for in each AZ for the based on the available spare capacity. You need to use horizontal pod autoscaler to scale your application, and cluster autoscaler to scale the underlying infrastructure. So remember, we are not using scaling policies within EC2 autoscaling. We are using these Kubernetes components. You can control the scheduling of your application with node affinities, taints, and tolerations. So you can control if you want an application to run on, or to force it to run on Spot, or to force it to run on demand, or in the likes. With AWS Node Termination Handler, we make it very easy for you to handle interruptions. As you have seen, getting it running is super fast with Helm. And it's very free, so you leave it running and it will handle the interruptions. And then with Cluster Over Provisioner, you can over provision your nodes, so you have some headroom in case the new pod, your application needs to scale and there is not enough room on your cluster. So these are low priority pods that in case application pods need to be scheduled, these are evicted and the application takes place. And then with pod disruption budgets, you can configure a minimum percentage of pods for your application that you want to be running all the time. So doing just 2 minutes warning, you can leverage the time to gradually move those pods of the same application running on the Spot instance to schedule replacement pods somewhere else. If you're interested, I also like to share with you that we have a public roadmap for our container services that you can find on GitHub, and that I encourage you to go and check. This is a great source for our development team to focus our development efforts. So in AWS, 95% of the features we build are because customers tell us that they need them. So this is a super important tool. And yeah, so before going to Q&A, I'd like to give you 3 pointers. One is the definitive guide to run EC2 Spot instances as Kubernetes worker nodes. That is a very detailed blog post written by one of my colleagues, Ron Sheinberg, that explains all the different practices we've talked about today. There is a very nice cost optimization blog post for Kubernetes with Spot that you can see on the link here. And also, our team publishes and maintains self-paced workshops you can find on easy2spotworkshops.com. So here you can find self-paced workshops that you can run on your own AWS account, and that show you how to use Spot instances with different use cases. One of them is Kubernetes, but we also have different workshops where you can learn how to use Spot instances with web applications, or with machine learning training with SageMaker, or with CI/CD with Jenkins. So I encourage you to go here and take a look and spend some time to see how things work in practice. And with that, thank you very much. If you have any outstanding question, please put it on the chat, and we'll address any pending questions or review common questions. Thank you.